Right, we've got a cubic and the point P, 5 minus 13, lies on C, and the line L is a tangent, just glances off of the curve at P. Use differentiation to find the equation of L, giving our answer in the form y equals mx plus c. So what we can do is find dy by dx, which will be 3x squared minus 20x plus 27. Then substitute 5 in. When x is equal to 5, because that is going to be the instantaneous gradient of the curve at x equals 5, but that is the same as the tangent. Three times 25, that's 5 squared, minus 20 times 5, that's just minus 100, plus 27, gives us 2. Okay, so that's the gradient of the tangent as well. Now I can write down the equation of the tangent. I can use y minus y1 equals mx minus x1, substituting these points in for x1 and y1. So y minus minus 13, or y plus 13, is going to equal 2 times x minus 5. We're asked to write it in the form y equals mx plus c, so I'm very nearly there. I'm going to get y equals 2x minus 10 minus 13, so 2x minus 23. Hence verify that L, this tangent, meets C again on the y-axis. So I just noticed that we've got minus 23 here as the intercept for C, minus 23 here for the intercept of the tangent. So both C and L, or the curve and the tangent, have y-intercepts of minus 23. Therefore, L meets C again on the y-axis. The finite region R, shown shaded, is bounded by the curve C and L. Use algebraic integration to find the exact area of R. Okay, so what we can do here is draw a line up from the tangent and find the area of this trapezium. And then I can integrate under the curve, which will actually give me this bit here, and then subtract them. So area 1 and area 2. Just be careful, because if you integrate, you're going to get a negative value, so we just have to deal with that. The trapezium will be okay with. So we know that this length is 23, because remember we just showed that the y-intercept was minus 23, and this length is 13, and then along here is 5. The area of a trapezium is a half a plus b times h. Parallel sides are here, so half 13 plus 23 times 5, which becomes, this is 36, so 18 times 5, which is 9 times 10, which is 90. Okay, then area 2 is going to be, well, it's the integral from 0 to 5 of our original function, which is x cubed minus 10x squared plus 27x minus 23. Now actually I'm going to put a minus, because that integral is going to be negative, so put a minus to the left of it. I'll then get a positive, and then I can subtract them. I wouldn't say that's a major deal, but technically speaking, if I'm finding the area, there should be a negative here to make the whole thing positive. Okay, well now we're asked to show, we can't just put this in a calculator, we need to show our working. So I get a quarter x to the 4. I'm raising my power by 1, divided by the new power, minus 10 over 3 x cubed, plus 27 over 2x squared, minus 23x, evaluated between 0 and 5. I can just put that in my calculator now, and to be fair, you could probably just do it using this function, but I'm not going to. So a quarter, or 0.25 times 5 squared, minus 10 divided by 3 times 5 cubed. Sorry, I think I just made a mistake. That should have been 5 to the 4 times 5 cubed. Okay, it's going to be that. When I put 0 in, I'll just get 0. So actually I'll get minus 37 and 11 over 12. Which of course is then 37 and 11 over 12. I did say I wasn't going to use the other functions. It's probably worth checking, okay? Even though we need to show it working, it's not going to take long to just do the integral using a calculator. And then again, we get the negative. So that's good. Can be pretty well, not pretty confident, very confident with that. And therefore the shaded area will equal the red area, 90, minus the green area, 37 and 11 over 12. And that just becomes 52 and 1/12. You could also leave it as a top-heavy fraction. So 625 over 12. Okay, nicely done. Well done.